Okay, welcome everyone to the August 10th, 2021 Open Planetary Lunch. Today's speaker is Michael St. Clair. I think this is your third return. There are benefits to being the closest collaborator to the person who organizes the talk series. The topic of the talk today is marslab, which is a Python library for multispectral image analysis. Abstracts away a lot of the math. I will resist the urge to give the talk myself since I also worked on it. But thank you for being here, Michael. And when you're ready, just go ahead.
All right. Okay. So hi, everyone. And yeah, so I'm here to talk about marslab. And as Chase just said, marslab is a Python library that's focused on the manipulation of multispectral imaging data currently. It's also a little bit of a grab bag. And I think I want to emphasize that we see it as also an ecosystem of libraries and applications that are designed to fill what we see as gaps in available functionality, or at least shared coherent functionality in this problem space. I'd like to note that we unsurprisingly see this as a natural partner to many packages in the Planetary Pi project. We have several stakeholders in that project here today, and probably an eventual Planetary Pi affiliate. So we have had marslab in development for about a year now. It's mostly been internal tooling so far. It's a support library for a variety of downstream applications, although we've definitely had valuable advice and contributions from external collaborators, including Andrew, who is here right now. Yeah, so the two largest downstream applications that marslab is a core support library for are unfortunately both covered by the Mars 2020 team guidelines, and we cannot demonstrate them in public. So it's a slightly awkward situation there, but in any case, marslab itself is getting mature enough that we'd like to discuss it a little and look for more users and contributors. And a fair warning on that point, the API shouldn't be considered stable quite yet, because although it's a critical dependency of other applications, we have complete development ownership of those applications. So we've had the freedom to break our own API as much as we want. It's only our problem. But this also means that we're really happy to have input still on the architecture of the library and even some of the shape of the outer shape of the API. Okay, anyway, let's look at some functionality. And so, like I said, marslab is currently focused on imaging data, and these are the easiest applications of the library to demonstrate because you can, look at them. I'm going to ritualistically ask if everyone can see this desktop okay. Great. And are you seeing, Chase, the entire desktop, not just the browser window?
Yes.
Great. Actually need that right now, but we'll want the rest of it later. Okay. So we will start by looking at some data from the MSL Mastcam PDS archive that I have stashed locally. And I'm also going to put this demo notebook in the dev branch of the repo later if you'd like to repeat any of this process. And as a note, here's a link to the necessary demo data files in Google Drive. Okay. So I'm just showing a list of what files we're looking at right now. This is a fairly boring Mastcam multispectral observation from the latter third of the mission with like a broken rock. I mean, it's not boring. It's a great rock. All geologists in the audience should note that yes, the rocks are irreducibly complex and beautiful in their own right. But it's a picture of a rock like a lot of other pictures of rocks we have. There shouldn't be too many surprises. So there are some useful text and file name parsing functions in marslab and its cousin library Dust Goggles for quickly skimming labels and paths and interpreting them without necessarily fully parsing their structure, which is great for organizing operations on really, really big file systems, especially networked ones, where you might not have time to correctly parse 300,000 to 1 million labels. So this is just parsing information from those labels in real time to make a metadata data frame. Tongue twister. So this is just, again, information right out of the file names or the labels. Using this metadata data frame, I can construct a marslab bandset object. So a bandset object is an abstracted representation of a single multispectral observation, whatever that means for a given data set, analysis, instrument, etc. In this case, and for most rover mounted filter wheel spinning multispectral cameras, it's probably going to mean something like the full spin of a set of filter wheels and all the images created thereby. It concatenates whatever data products make sense to analyze as a coherent unit. And there's some shared logic that can be applied to a lot of different kinds of multispectral data on the parent class. And then there are also subclasses created that silo specific behaviors and facts about instruments, and also reference our compatibility module, which contain things like very boring instrument definition type stuff, like what are the canonical center wavelengths of all of the color filters on each eye of MSL Mastcam, that kind of thing.
Michael?
Yes.
Just to understand this further, your info filtering has many files. So one observation has many files, and this is because it's more than one filter, or it's because the observation has a wider definition of several data files?
So in this particular case, for MSL Mastcam, the individual filter images are stored in separate logical files. Yes, like separate .img files. And however, as I'm about to demonstrate a little more visually in a minute, these different filters tend to be analyzed at the same time by instrumentalists and geologists.
Okay.
And so
that's actually similar to the multi-sensor data set of the high-rise camera, where
absolutely.
all the channels. Okay, good, thanks.
High-rise is another natural application or natural instrument to apply this to 100%.
Cool.
Okay, so we have all of these filter images, and so we have this bandset object, and I'm just going to note that it's pulled in information about how these logical bands are logically arranged within the corpus of files that is being referenced by the bandset object. So that includes things like, let me back up. Each of these entries in band and filter are the canonical name of a particular bandpass of Mastcam. So all of the bandpass names start with L or R, depending on whether the filter is on the left or the right eye of the camera. Then a kind of arbitrary 0 through 7 assignment. They're not increasing in wavelength on Mastcam as you might expect or anything like that. It's kind of how they wanted to do it. 7 is only used for atmospheric observation. It's like a very long IR filter and very opaque and is not typically included in these observations. And 0 is the clear filter. So after that, we append an R, a G, or a B for information that we pluck out of the individual Bayer array elements from shots taken through the clear filter. So we have the name of the band, the human readable name of the band. We have the canonical center wavelength of the band. And then we have the logical position of that band within whatever file is referenced here. In most of these cases, these are single band files, so we don't give it a specific index pointer. For the Bayer, for the clear filter images in particular, these are debayered on board for Mastcam. So these are two separate files, L and R, each with 3 bands. And so the band set object contains pointers. Does that make sense, Michael?
Yes, yes. It seems that the index number then is only defined for the final RGB image.
In this case, yes, because these are all single band files. So it just takes the band that is there. For clarity, I could also fill these with zeros.
Yeah, okay.
Okay, so bandset exposes a variety of loaders, which are interfaces to actually like pull the data out of files. Currently, I have ones written that leverage Rasterio, Pillow, and PDR. PDR is the Planetary Data Reader. It is a separate PDART funded project. Michael is also involved in that. Chase is involved in that. Its goal is to offer a single endpoint for reading all of the data in the PDS. And in this case, we're using it because we need information from the detached PDS3 label to interpret these binary arrays. So you can see that this band set has a reference to the PDR load object with some information about special constants, and then just go ahead and load the images in. And raw images are then stored in a dictionary that is an attribute of the band set object, which is just a dict of string to in the array. So yeah, that's one array for every logical band. So we still have some problems here, of course. Like some filters on Mastcam, the narrowband filters, fall within the band passes of the camera's Bayer array. So we get effects like this from these data. We have, like 1 out of every 4 pixels because we put a screen door in front of the science instrument. Fortunately, because this is an ongoing and perpetual annoyance, we have placed a lot of functionality in marslab for this specific case. You can tell it facts about a Bayer array, like what Bayer pixels a filter might be hidden behind, and like a logical sort of discrete mathematics description of a Bayer pattern. And then you can use that to greedily bulk debayer everything. So this happens in real time. This is debayering all of the images. And as you see, the pattern is gone. Are there some artifacts left? Yes. Are there Bayer artifacts left? No. It is at least as good as we can make it. And this uses a very, very fast and we think usually correct, greedy non-kernel based bilinear interpolation. And now from now on, the get band and related functions will return what it thinks is the most reduced, most correct version of any individual band. Okay, so what do we do with these? So let's say that you're a geologist who is interested in various spectral parameters of these images, and you would like to figure out where to draw regions of interest, to determine spectral end members, and maybe, if you're lucky, identify material composition within the image. Now you could handcraft code to create each one of these parameter maps, but perhaps you would like a whole bunch of different parameter maps that might or might not be useful on an individual image, but which you would like access to at all times on your many images. So to this end, marslab implements a system for generating what we call looks, which are based on a variety of common rendering techniques used for multispectral data, including very simple things like arithmetic spectral parameters. Looks are described in valid Python code that is also intended to serve as pseudo markup. So this is intended to be relatively easily readable and editable by people who are domain specialists, but do not spend a ton of time reading or writing code. So these are really simple look descriptions for 3 image types that are commonly used in the MSL MassChem publications. So a parameter map of band depth at 527 nanometers. Band depth is a parameter used frequently in reflectance geology to describe the amount that a given point deflects upwards or downwards from a notional continuum. So like the deepness of a trough or the sharpness of a peak. So band depth using these bands, a name so it can be referenced. This is a decorrelation stretch, which is a simple dimensionality reduction into the RGB space based on 3 bands, and quote unquote natural color, which is just going to be a composite of the 3 left eye Bayer filters. So more or less like what a commercial camera is doing. And then we can make these as a group, like raw images. These are cached in a dict. Just look at these all real quick. Happening in real time again. Here they are. So here is the decorrelation stretch, natural color, and the slightly boring, but perhaps indicative and useful band depth map. Okay, great. So that's fine. And as you can see, that's fairly readable. It's easy to change if you decide that, in fact, the correct shoulder for this should be L3 or whatever. Can be contained in a separate config file, edited relatively easily by people who don't necessarily have to touch the rest of the code. This is very useful. Okay, but what if perhaps we would like to do something much more complicated than this? Well, the markup provides an interface to a subset of a flexible informal function composition toolkit with a whole bunch of special logic for visual rendering. So you can assemble complex stretches and representations of multispectral data very easily. Oh, and I should recall that please note that this relies, especially as I'm continuing here, on the implicit ordering of dictionaries in Python 3.7 and higher. You would have to do a certain amount of hacking to make it work in older Python. And ideally, marslab is intended for Python 3.9 and above. That being said, I'm just going to pull out this like little template I wrote earlier for spectral operation defaults. We've got a quote unquote limiter in here, which applies a sigma clip to pull things into an easily visible space. We apply a little Gaussian kernel, and then we plot it in Matplotlib with a diverging color map I'm very fond of. And then we will go ahead and write out 3 separate spectral parameters: band depth at 527 nanometers, band depth at 827 nanometers, and the ratio of bands R6 and R2. And then I just insert this template into each of these dictionaries. Great. And then, okay, let's say also we would like these in a non-diverging grayscale. And then also there's this other instrument that produces all of their maps in rainbow scales, and we need to compare our data to those rainbow scales. So we got to generate some rainbow scales too, perhaps against our better judgment. So just add that in real quick using little generation expressions. I'm going to add a Matplotlib instruction to the decorrelation stretch instruction, and then I'm going to make a more boring version of that as well. I'm going to do the same thing by adding a Matplotlib instruction to the natural color look, and then I'm going to make an enhanced color look that fills the color space in each of the channels individually. Okay, and there's all our looks. Cool. These are our looks. Here's what the individual looks look like now that they're assembled into these dictionaries. I'm going to destroy our cache of looks, and then I'm going to make these looks. So this supports multi-threading, but it does not work well in a REPL environment, so I'm not demonstrating it here. So I'm sorry that this is so slow. Okay, a very long time to generate all these. All right, sorry about that. And here they are. So you see we have these beautiful diverging scale band maps. I love this orange teal map. I think it's very expressive. It's designed for like almost maximum accessibility to if you have color vision in almost any part of the color space. you should be able to distinguish this teal and this orange. We have our rainbow versions of these maps. We have our familiar natural color. We have our enhanced color. We have the gray non-diverging versions of these maps. And we have our quote unquote exciting DCS and our somewhat more muted, sadder DCS. So one thing actually that I want to note real quick is, let's see. Say the jet is good for it. On almost all of these, you might have noticed that you see a huge difference between the center and the edges of the image. One thing that's becoming that just becomes immediately visible here when you look at all of these spectral parameters is a calibration problem with MSL Mastcam's lenses that's corrected, like flat fielded out in some of the data, but has not yet been flat fielded out in these data. And this is one thing I like about being able to generate a wide array of slices and stretches on data like this really quickly, is that you can see patterns within the data set intuitively and viscerally, because it happens so quickly and makes itself immediately available in an equipmental sense. Cool. So there's nothing actually Mars or rover specific about marslab. So I think we were talking about orbital data a little bit earlier. This is a simple version of a band set that I've made for the Clementine orbiters, UV-Vis, and near mosaics. So this is a single frame of the Clementine UV-Vis mosaic. And what this is in particular, this tile is Tycho crater and its immediate surroundings in these 5 bands. And this is a case where the entire observation tile is contained in a single file. They have a single 5-band file, or in the NIR version of this data set, it's 6 bands. But so we do not give a whole bunch of files to this band set. We just give it one file, and it has rules for like assigning wavelengths to every band of that file. Okay. And then I'm going to define some default spectral parameters for these data as well, which is mostly the same, except I'm including a whole bunch of these different weird special constants that are in these data. Screw everything up. You don't account for them. Similar, except I'm picking meaningful bands for 2 spectral ratios, some decorrelation stretch rules. Great. Okay. And we have some beautiful, and again, I think highly expressive lunar orbital data. Effects that might be either geologic or illumination geometry related show up really quickly in the decorrelation stretch around the edges of craters, which I think is quite interesting. And features that are almost certainly geological, although which might be related to rock distribution or regolith coverage, are readily available in the parameter maps at surprisingly quick and high resolution. Lovely. All right. And then finally, I would like to mention that there's a subclass called Imagebands that is designed for simple multi-band operations on consumer image formats, which uses pillow and takes the channel names of the color space as the names of the spectral bands. This is a page from a medieval astronomical manuscript. Here are each of its channels individually, RG and B. And so here, Imagebands just sort of reductively looks at it. It opens it with pillow. It's like, hey, pillow, like what color space is this in? Okay, each of those is a channel. Great, we'll pretend it's a thing. We're using the pill loader. We've got it. And then we can also perform this kind of spectral operations on images like this.
Michael?
Yes.
I just saw that your index values were now RGB, while before they were 0, 1, and 2.
Yes, that is because pillow. It is because the pill loader uses like Pillow's get channel rather than indexing into the array.
Okay.
Like an array that does not yet exist and that may not in certain formats exist until Pillow has loaded it. Does that make sense?
Well, I mean, I know the situation of wrapping things that are having suddenly a different idea than the layout of your framework you created. I just can foresee that this might be confusing to the user what to use when. You would need to know this, right?
I think when we refer to bands in these images, we use band. I think in general do not use index. Index is just there as a reference to the file format.
Exactly, index is for the loader.
So maybe the end user should never use IX, you say?
Unless they need to define special behavior for a specific data set. If someone is using Imagebands, Imageband populates that field based on what Pillow tells it about the channels.
Okay.
The channels not all channels in like consumer compressed image format color spaces have a natural ordering from like 0 to n. That's so defining that prima facie is problematic. But yes,
Whereas,
go ahead.
Also, one of our assumptions in a band set object is that each of the bands appears once, or at least each band I combination appears once. You can sometimes have instruments like MassCam, MassCam-D, where both eyes are capable of observing the same wavelength.
Yeah,
but
exactly.
That would still, the band name would still be unique.
Yes, and band is intended to be the human readable name. IX is a reference to the loader.
Okay, thanks.
And is auto-generated in this case by Imagebands. So let's look at this look in more detail. So what is this? We have you can see each of its steps. And here I'm looking at the look object that I have compiled from this instruction rather than passing it directly to the band set. When I pass it to the band set with the make look set method you saw earlier, it does that compilation behind the scenes and then renders the looks. Here I've compiled it as a standalone object that I can inspect. So I see the functions that it is wrapping, which are a partially applied version of this spectrum operation look function and a partially applied version of this sigma clipping function and a partially applied version of this matplotlib function. And I can see some of its meaningful or readable parameters as well. And then I can take this look object and I can just feed it the data myself rather than sending it through bandset. And note that I could be feeding it other data as well, which don't have to come from a bandset. But also, if we want to interact with looks on this level, we can manipulate them at runtime flexibly and dynamically. So for instance, perhaps you would like to cache an individual step of this rendering pipeline. I'm going to add a capture point to the limiter step. Then I'm going to go ahead and execute this again. And so we've got that, great. And then we can look at that capture point and what have we got there? Well, it's an array. It hasn't been rendered into a matplotlib figure yet. Hasn't been color mapped. And it is a black and white pre-color mapping, but post-clipping, post-sigma clipping version of the image. Similarly, we can place callbacks into these looks. So for instance, if I didn't want to do those steps manually, but I instead wanted that rendered out, so that I could look at that intermediate step to diagnose a problem, or because it was a valuable product in its own right, or for whatever other reason, I and place a send here. A send is a pipe from a given point in this function pipeline to some external function or composition of functions. In that case, both of these things will render. We'll render at the limiter step and then also at the plot step.
Michael,
Yes.
what triggers the send? What interaction?
So in this case, when I call execute,
Oh,
it's
okay.
popping through like every point in the pipeline, and that point had had a send attached to it by then. So if I don't execute this, and just compile it here, or do many. You'll now see if you inspect this, that there's a send on the limiter step. And so you can expect that after the completion of the limiter step, the output is going to be sent to this send and then continue down the main chain.
So the Eclipse raw band is being fed to the imshow function, correct?
The Eclipse raw band is being fed first to look, which is the first step
Okay.
in steps.
Okay.
Then the output of that is going to limiter. Then the output of limiter is going to plotter, but also the output of limiter is being sent to this send imshow.
Oh, okay. Very flexible. Yeah, cool.
Yeah. The metaphor here is from like an audio mixing console. It's not actually designed for that type of real-time audio signal processing, but like if you are familiar with, say, also like assembling a guitar pedal board, it's that kind of logic.
You might have just explained to me half of the audio digital workstations. I never got what they mean with that scripting language. I think now I get it.
All right, good. That wasn't the direction I intended that explanation to go, but if it means that you're, knocking out some sick beats, that's wonderful. That's a good outcome too. All right. And I would like to note that these pipelines, these look pipeline objects, can also be lazily evaluated. So if you'd instead rather just like look at each step as it comes. So this is the generator, and it's gonna yield each step of that pipeline. So this is the initial spectrum operation after sigma clipping, and then the plot. I would like to emphasize that this look has a bunch of internal logic for image rendering, or special cases, perhaps I should say, for image rendering, but it sits on top of this other library composition, which is not just a plotting and visualization tool, but rather a kind of highly flexible, impure function algebra on directed graphs. Informally formal, sort of. So if I wanted to say, take this skewed normal distribution, and then I'm going to build this composition, which is the parent class of look. And you make 3 steps that are clearly named. There's a step that tiles, there's a step that horizontally mirrors, and there's a step that plots. And I execute it, initializing it down the chain with that array normal. Now this will fail. I'll fail for a different reason because I should run that cell. But this will fail because numpy.tile lacks required positional argument. But in addition to the other methods of manipulating compositions, which include looks at runtime I've shown you, you can bind arguments to objects after initialization. So here I am going to make 10 closely related copies of this little pipeline composition. And so the even numbered ones are going to tile horizontally, and the odd numbered ones are going to tile vertically. And ones that are divisible by 3 are going to plot in that orange teal diverging color scale I like so much, and ones that are not divisible by 3 are going to plot in Matplotlib's well-loved Viridis color scale. And then we are also going to add a trigger, which is like a send, but does not take any of the data, to the tile step that creates a new matplotlib figure, so we will not continue writing into the same figure over and over and over. And then I will add another trigger at the end to create a color bar on each one. And then I will make an iterator out of these 10 compositions. So now I have this iterator of compositions, and now I'm going to start executing them, and it's going to be exactly what you'd expect. We have there, and now it's orange and teal, which is great, and it's vertical again, and it's horizontal again. It's vertical and orange and teal now. That's great. And here and here, and we're out. So you can use this logic and the functionality enabled in look in its parent class composition to create these highly flexible, highly portable, introspectable, reproducible processing pipelines, which can be very, very big or very, very small. And I want to doubly emphasize that even though I just showed you pictures, again, this is not just an imaging tool ultimately. Also, like, here's a composition of addition and multiplication. I'm going to add points to insert arguments. Great. I'm going to execute it with 1 plus 1. That output sent times 2. 1 plus 1 times 2 is 4. Thank you. I've solved mathematics. And then as a slightly different and mildly less contrived application, let's say that I wanted to cobble together some kind of contained in object text manipulation script. Like there's some problem in my code base where the name of the library has changed because someone broke an API. Probably it was me. And I'm going to fix all the imports with string substitution. So this is basically like the kind of thing you do in a shell script, or like if you were a sensible person inside an IDE, but this is a contrived example, so you're not. So I'm going to define this function head, which is like new core utils head. It's going to give us the first size characters out of a file. And then I'm going to make this little composition sed, which its first step is head. So it's getting the first size characters out of a file. And then it is going to substitute using the Python standard library regex substitution function, some string for some other string that it finds in there. And then it's going to print it out to our REPL environment. And then I'm going to bind the argument 100 to the head, bind the argument import, and actually like fixing the library, like why do I want to fix this import? Why would I want to import anything? Dependencies are terrible. And then just so I know what things looked like beforehand, I'm going to add a little send to head, and then I'll execute this on just a random Python script here. And so you see previously we had something that looked like this. But this substitution composition, this string substitution composition, sed performs these string composition operations. And let's say that I become less doctrinaire in my thinking about dependencies at runtime, and would like to, instead of raising an exception whenever I tried previously, short-sightedly to import something, I instead simply import marslab and old and new. And that's that example. And that is the last example I wanted to share with you. And I'm now opening up the floor to questions.
I think everyone knows the policy that if you have a question, just unmute yourself and ask it. Michael, I had a few in the chat, which I'll let him say.
Yeah, so going backwards, fresh in memory, there's the steps that you just entered there, or like a sense, could be any Python function. So it could be also a color series or PySys, an ISIS processor that could be part of it, right?
100%. Yep.
Okay. And then going back, what did I have? Yeah, the instruction, which seems to be some kind of meta language definition for easy to use. What is the requirements on an instruction before it can be used? Is like a minimum set of parameters? Like, for example, you had this one, stop. Yeah,
This one,
or yeah, any of these bigger ones. For example, I was wondering, do I need to have the plotter in the instruction before I can use it? I guess not, right?
no, you do not need to have a plotter. The only thing that look in particular needs is a look. So it wants some core idea of what it's doing at all. Composition doesn't require anything. Like if you just initialize composition with no arguments, it will send you back a composition that contains just the identity function.
Okay, and the instruction set here is, what do you call it? You call this object an instruction dictionary?
Yeah, instruction dictionary is good, or a single instruction would be a way to
Okay,
talk about it. And yeah, it's a Python dictionary that needs to be valid Python code, but is designed to be pretty abstracted.
yeah. No, I was just wondering what makes this a look, just the fact that it has a look keyword?
And it becomes a look after we compile a look using, this.
Ah,
Yeah.
okay. And so if it doesn't have a look in there, you can't give it to the look object, to the look
No.
creator, right?
No, look,
So do
will
you
get
already
bad.
have, do you have already other use cases for these instructions apart from looks?
Well, I showed a couple of examples down here that were slightly contrived, but I do have, yes, also not contrived other applications for composition.
Uh-huh. Composition is another use case for instructions, right? That composition is not a look.
No, composition is not a look. Composition is the parent class of look. And composition itself will take very, very similar instructions. Look knows more fact about how to assemble a request for a spectral parameter into a sensible list of functions.
Okay. And then my last one is, because I have similar design questions in some of my code as well. I noticed that you have an mcam band set and a clem band set class. What is the specialization you apply to these classes that makes them a clem band set versus, is there some instrument specific code or hard-coded strings that need to be in there so that it knows where to look certain calibration defaults or something like that? What's your specialization between these classes?
Yeah, and some of that is actually contained in the compatibility module as well when we want to access it outside of band set. So like the Clementine is a little bit of a stub. I basically made it for this demo. But so the Clementine compatibility module contains the fact about like all of this enormously large number of special constants that the Clementine mosaic tiles use, and then the canonical mapping of the wavelengths to the filter band names. And then the Clementine band set object itself, I note that, so here's the name of the Clementine data set. Here is like a rule about accessing the band and index based on facts I know about the data sets, the NIR and the UVviz data sets, et cetera. A very small amount of logic in this case, but important to get it right. I also assign a particular loader. There's considerably more logic on the Mastcam band sets because we've built these out more for applications, but it's still not super extensive. But it's stuff like, how do we deal with the fact that there are these two eyes? That kind of thing.
Yeah, okay. No, yeah, that's interesting. I mean, that's always the case on how you specialize these classes and how much you want to generalize or how much you leave to the class code itself or to the application functions to reset, put in, it's like left eye, right eye.
Yes.
Something. So yeah, interesting.
So Andrew, let's see. No, so the syntax is not from a specific concept or paper. Yes, it is a functional domain specific language. However, we would like to keep the syntax for that language fairly verbose and expanded, because we would like it to be something that is accessible and sort of not look like code in a lot of externally loadable files. I like S expressions too, and I also like Lisp. And yes, in fact, what a lot of this does is create like composed directed acyclic graphs. It is a slightly more informally, and there are ways to cheat, so it's not a real algebra of that kind, but it is sort of like an algebra of that kind, but we want it to be wordy.
Yeah. I mean, I was just like, I think I was like looking at some, like there's some places where there are like 4 comprehensions and like deep copies of dictionaries. And like, I know some of that's for the demo, and not a knock at all of what you've implemented for sure, but that just might be the most pragmatic way of implementing it now. But I think that's like when I immediately look at that, it's like, oh, okay, that's not necessarily easier than someone who's used to like imperative programming, MATLAB. Or
I wouldn't actually expose this part to the user in general, to be clear.
But that being said, like a lot of those things are like simple patterns and can easily be, I think, abstracted away in a way that works. I think it'll also be, I think there's some good things about using dicts here. I think also might be helpful. Maybe, was there a place down where you pass like a function name by a string?
Yeah, you can, in some cases, pass function names by strings. Yep.
Yeah. So like just being able to direct because what do you have to do then? Eval, or do you do a dict lookup to the actual like numpy function or something?
Get attribute would work.
Yeah, whenever I'm passing a function name by a string, I'm using getAttr of some module.
Right. Which works. But yeah, it just like it just like tickled some like previous memory that then led me to like get up this S expression stuff, because I've used Scala before in the past, and there's a lot of domain specific languages which can be
I like Scala too.
Expressive and useful. So
no, you're right. I should think harder about whether or not I would actually like to collapse this syntax more, because in the ways that I have so far deployed this, so like stuff like this is happening somewhere, but is not being exposed to the user.
Yeah.
Like instead, like we have this, variable grays, or actually like maybe we have like a thing like different colors, like that are, and anything in this list is being, like in an abstract, hidden from the user way, used to generate looks like that. Yeah. But there might be a way that I could collapse some syntax into a highly readable shorthand to expose functionality like this without making people look at a whole bunch of list or dict comprehensions.
Yeah. And I think my other question I'd like to was about the serialization. This is something I've kind of thought about, multiple different ways, like over the past few years. And then like I went one way with ASAP, where I'm using Jupyter notebooks to like encode Bash and Python calls in a workflow, and I treat the Jupyter file itself sort of like a make file. And it's running that, right? So like going up, like looking at the comments, like how do you envision like how the pipelines are shared? Is it just like copying the dicts around? Or like, can you compile and then export like the Python file that's just like, yield the imperative Python code, and you hand that to your colleague who might be more MATLAB focused, and like, okay, I understand X equals A, right? Like you basically render your workflow as like a compiled, well, not compiled, but a final.
I mean, compiled in a sense, not bytecode compiled, but yeah.
But it's interesting because like there's different ways of thinking about it, and just curious, like
I have mostly been
how you thought about it.
I've mostly been thinking about, these are things that would be shared as text files. Yes. And we have people who share them will have a notion that their execution environments will be similar enough that will be more or less okay. But de facto, within the code, or within some of within parts of the code bases that use composition, there are points where compositions are in fact being serialized and passed around between processes.
Mhm.
So I'm actually doing that. So I should consider whether or not I might want to support end users doing that in a more programmatic way. But I've been thinking about it as text. Yeah.
Yeah. Okay. Just curious.
No, cool. I really appreciate any feedback you have.
Yeah.
So sorry, I was just off for a few minutes, but I just had the idea, maybe you just mentioned it, that this separation into this dictionaries is of course ideal if one ever would want to make a GUI out of that. So
Yes.
it's kind of already very useful.
That's a very good point. Thank you. Anyone else?
And Michael and I do have a hard out exactly at 3. So if anyone has a really good question that can fill 4 minutes, now's the time.
I just
right.
was.
Yeah, go ahead.
I just was quickly wondering about your ability to put this out in the public being a dependent thing on your MAS programs.
All data that is available. So everything in this repository has been placed into the public domain already, well before we touched it. So like the demo data I just showed you is from MSL Mastcam from something like 2 years ago. It's archived in the PDS. None of the functionality here is functionality that has not been used in public, or sorry, none of the logical operations or ways of thinking about or talking about data or specific figures about the instruments or the data are things that have not been published.
Yeah, I was more worried about the intellectual property of all this work that potentially was financed by the project. It's like, do you have a deal that all the code that you produce within this project can be open sourced under MIT or something?
Yes.
I see. Cool.
It's all, everything we're doing for all of our projects for Million Concepts, we insist as a condition of our involvement that we can open source anything that's publicly funded.
Cool, very good.
Specifically, this is
so there are other things that, there's other software that we're writing for the missions, for example, that we can't share yet, but eventually that will all become public. It's all under BSD3.
So yeah, the issue with publicizing it is all confidentiality agreements like the M20 team guidelines, not IP issues. There's
yeah. Okay. All right, thanks much.
All right.
Very exciting.
For listening.
Thank you everyone for being here. We'll be on Slack if you want to talk about this more. We invite contributions. Andrew's already made one. So.
Yep. And Andrew also made a bunch of really good suggestions, and I would like to hear more of those type from anybody. So, all right. Bye.